we can predict the y value for a given x value in regression. Now the warning is to not provide any type of estimate for your response variable y unless the x value is in the range of the data you use to create your line of best fit. It's very dangerous and you should avoid making this mistake. This is called extrapolation. So after you have found that x and y are correlated, so you've done the hypothesis test and found a significant relationship between the two quantitative variables, then you may provide prediction estimates as long as you do not extrapolate. So suppose that we wanted to know how much would a wolf weigh if this wolf had a tail that was 16 inches long. So the first thing you do is you go to your scatter plot and you look for 16 as a tail length. Now notice you've got some tail lengths that are shorter and you've got tail lengths that are longer than that 16, so it's going to be okay to provide this estimate. Now as a point estimate you might think, oh well, I could use the equation of a line, stick in my 16-inch tail length, and then solve to get an estimated weight. So we could go back to our regression equation, which was weight was 48.4 plus 2.5 times the tail length. Substitute 2.5 times 16 is 2 16ths, right? So that'd be 32 plus half of 16 would be 8, so that's the 40. So 48 plus 0.4 plus 40 would be 88.4. So I might say, you know, on average, I would expect that wolves that have tails that are 16 inches long would weigh 88.4 pounds. But if you think back to what we've been doing, we don't really estimate values with one number, right? We do confidence intervals. Okay, so what we want to do next is, okay, how would we come up with an interval estimate instead of a single number? Well, what we do is we ask the software to produce this table of what are called predicted values. So for the x value, that would be your tail length, for 16 inches, it predicts the y value as 88.7. Now the reason that's different than the 88.4 is because in the software, when it fit the data and found the line of best fit, it actually kept more digits in the background, and I just rounded those off to the 10th digit for ease of display and everything. But if we kept all those digits, we could get that same number. The SE prediction of y is sort of an estimate of the standard error when you're predicting, and then you've got two different intervals. You have a 95% CI or confidence interval for mean, and you have 95% PI, which stands for prediction interval for nu. And the idea is, okay, there are two different estimates we want to be aware of and then distinguish between how we estimate those two quantities. So let's think about the two possible estimates. We could be desiring an estimate for the weight of a single wolf that has a 16-inch long tail. In that case, we're estimating for one animal, how much would this one animal weigh if that one animal has a 16-inch long tail. Now the other estimate would say, let's consider all of the wolves that have 16-inch long tails. What would the mean weight of all those animals be? Okay, so the idea is similar to what you could do with a normal probability question. I could say, hey, suppose that you've got the fill amounts of soda in cans that's normally distributed. What's the chance a single can has maybe more than 12 ounces of soda in it versus let's take several cans and talk about the mean, right? So what is the probability 10 cans have a mean value of more than 12 ounces? So what happens is in the first normal probability question you're using sigma in your z-score, whereas in the second one you've got what? Sigma divided by the square root of n. So your standard deviation or your standard error is a little bit different based on whether you're estimating a single outcome or a mean of several outcomes. So in our example, if you want to estimate the weight of a single wolf that has a 16-inch long tail, that's what we call a prediction interval. It's like you've taken some data, you fit a model, and now you say, hey, here's this other wolf that has a 16-inch long tail. How much do I estimate this one wolf to weigh? Now you might realize that a single value, a single wolf, is going to have a wider range of weights than if you're estimating the mean of a lot of wolves, because the mean is not going to be impacted as much. It doesn't vary as much from sample to sample, if you want to think of it that way. So the second case, the confidence interval, the CI, is where you would use that interval if you're estimating the mean weight among all wolves that have 16-inch long tails. And again, even if you have some wolves that have longer or shorter tails in different weight classes, or for all 16-inch long tails, some wolves are heavier or lighter, but on average that mean isn't going to be as variable as an individual weight of a wolf would be. So the confidence interval is going to be narrower. So then what we want to do is go back to our chart. So we're at the top line where the X value is 16, and in the first case we're estimating for a single wolf. So we want to use the 95% PI. So that would be the 52.2 to 125.2 on that line. So I would just write a summary that says, with 95% confidence, the weight of just one wolf that has a 16-inch long tail would be between 52.2 pounds and 125.2 pounds. Now in the second case, we're talking about the mean weight of all wolves that have that characteristic of a tail being 16 inches long. So we are 95% confident the mean weight of all wolves that have 16-inch long tails would be between 75.0 and 102.4 pounds. So notice the difference in the PI and the CI there. Now suppose that I went back and I said, I want you to estimate the mean weight of wolves that have tails which are 30 inches long. What would your answer be? I suggest pausing the video, thinking about what you would do, and then going on to the next slide. Did you check the scatter plot first? Remember, we don't want to make any predictions about wolves and their weights unless the tail length we're dealing with is within the range of values we use to fit our line. Now the shortest tail length was about 10 inches. The longest was only about 27 inches. As a result, 30 inches is actually too long of a tail length for us to use. So it would not be appropriate to provide that estimate. Now let's go back and suppose that I asked you to estimate the mean weight of wolves that have tails which are 24 inches long. What would your answer be now? Okay, in this case 24 inches is okay to do the estimate. So now what I need is the CI, because I'm estimating the mean for all wolves which have an X value, a tail length of 24. So I'm on the line in the middle of this chart where the X value is 24, and I want the CI. So that's the 95.2 to 122.6. So I would say I am 95% confident that the mean weight of all wolves that have 24-inch long tails would be between 95.2 pounds and 122.6 pounds. So this is the way that you do estimation using your regression line.